Welcome to our exploration of one of the most captivating and enigmatic phenomena in the universe, white holes. To understand white holes, we first need to delve into the realm of black holes, those dark, gravitational beasts that have captured the imagination of scientists and the public alike. Black holes are regions in space where the gravitational pull is so intense that nothing, not even light, can escape from them. They form when massive stars exhaust their nuclear fuel and collapse under their own gravity, creating a singularity surrounded by an event horizon. This event horizon marks the point of no return. Once anything crosses it, it is irretrievably drawn into the black hole's depths. The study of black holes has transformed our understanding of physics, challenging our concepts of time, space, and even reality itself. Now, imagine the opposite of a black hole, a white hole. While black holes consume everything that comes near them, white holes are theorized to expel matter and energy, making them the cosmic counterparts to their darker siblings. In essence, a white hole is a region of space-time that cannot be entered from the outside, but from which matter can be emitted. This idea may sound bizarre, but it arises from the same equations of general relativity that describe black holes. The theoretical significance of white holes lies in their implications for our understanding of the universe. If black holes are gateways to singularities, could white holes be portals to other universes or dimensions? What does this mean for the fabric of space-time and the laws of thermodynamics? These questions ignite the curiosity of physicists and cosmologists as they search for answers within the tapestry of the cosmos. In this report, we will explore the concept of white holes in depth. We'll examine their definitions, the physics that supports their existence, and the current state of research surrounding them. We will also discuss the implications of white holes for our understanding of black holes and the universe at large. Join us on this journey as we unravel the mysteries of white holes, challenging our perceptions of time, space, and the very nature of existence. By the end of this report, we hope to illuminate the fascinating world of white holes and inspire further exploration into the wonders of astrophysics. What is a black hole? Welcome back. In this segment, we'll unravel the mysteries of black holes, one of the most intriguing phenomena in the universe. Let's dive into what black holes are, how they form, their defining characteristics, and their significance in the fields of astrophysics and cosmology. At their core, black holes are regions in space where gravity is so strong that nothing, not even light, can escape. This profound gravitational force arises from the collapse of massive stars. When a star exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. The core implodes, leading to a point of infinite density known as a singularity, while the outer layers may explode in a spectacular supernova. The boundary surrounding a black hole is called the event horizon. This imaginary sphere marks the point of no return. Once anything crosses this threshold, be it matter, radiation, or even light, it is irrevocably drawn into the black hole's depths. To an outside observer, anything crossing the event horizon seems to freeze in time, gradually fading from view due to the intense gravitational effects and the bending of light. Black holes can be classified into several categories based on their mass. Stellar black holes form from the remnants of massive stars and typically range from about 3 to 20 times the mass of our Sun. Supermassive black holes, found at the centers of galaxies, can contain millions to billions of solar masses, influencing the dynamics of entire galaxies. There are also intermediate black holes, which are still a subject of active research, and primordial black holes, theorized to have formed in the early universe. The importance of black holes in astrophysics and cosmology cannot be overstated. They challenge our understanding of physics, particularly our grasp of gravity and the fabric of space-time. The study of black holes helps us explore fundamental questions about the universe. How do they influence galaxy formation? What happens to matter inside a black hole? And what does their existence tell us about the nature of time and space? Moreover, black holes serve as natural laboratories for testing the predictions of general relativity. Einstein's groundbreaking theory that describes gravity as the curvature of space-time caused by mass. Observations of black holes have provided crucial insights, particularly during events such as the first ever image of a black hole's event horizon captured by the Event Horizon Telescope in 2019. As we continue to study black holes, we uncover not just their secrets, but also the broader workings of the universe. They act as cosmic anchors, influencing the behavior of stars, galaxies, and even the cosmic web of structures that make up our universe. In summary, black holes are not just cosmic vacuums. They are fundamental components of our universe that challenge and enrich our understanding of the laws of physics. Their formation, characteristics, and the mystery surrounding them continue to inspire scientists and enthusiasts alike. Definition of white holes. A white hole is essentially a hypothetical region of space-time that cannot be entered from the outside, but from which matter and energy can be emitted. In simpler terms, if black holes are cosmic vacuum cleaners, sucking everything into their depths, white holes are imagined as cosmic fountains, spewing matter and light into the universe. This concept arises from the same equations in Einstein's general relativity that predict the existence of black holes. The opposite of black holes. To understand white holes, it's crucial to first grasp the nature of black holes. As mentioned earlier, black holes form when massive stars collapse under their own gravity, creating an event horizon beyond which nothing can escape. In contrast, white holes are theorized to have an event horizon that does not allow anything to enter. Instead, they are seen as the final stage of matter expelled from black holes. This intriguing dichotomy raises profound questions about the nature of the universe. If black holes are endpoints where matter is lost to the cosmos, could white holes serve as exits for that matter, potentially leading to other regions of space-time or even other universes? This notion aligns with some speculative theories in physics, suggesting that black holes might connect to white holes in a form of cosmic tunnel or wormhole. Theoretical basis. The theoretical foundation for white holes is rooted in Einstein's field equations of general relativity, which describe how mass and energy warp spacetime. When these equations are manipulated under certain conditions, they can predict the existence of white holes. However, it's important to note that unlike black holes, white holes have not been observed. Their existence remains purely theoretical. Some physicists propose that white holes could be linked to black holes through hypothetical constructs known as wormholes. These theoretical passages through spacetime could connect a black hole in one region of the universe to a white hole in another, offering a potential means of travel between distant points or even different universes. However, the stability and practicality of such wormholes are still subjects of intense debate among scientists. Additionally, the thermodynamics of black holes implies that if black holes lead to a loss of information, known as the information paradox, white holes might represent a mechanism for information to be expelled back into the universe. This raises profound philosophical and scientific questions about the nature of information, entropy, and the fate of matter in the cosmos. What is time reversal symmetry? At its core, time reversal symmetry is a principle in physics that suggests the laws governing the universe remain unchanged when the direction of time is reversed. In simpler terms, if you were to watch a movie of a physical process running backward, the fundamental interactions would still hold true. For instance, if you see a glass fall and shatter, time reversal symmetry implies that you could also have a scenario where the shattered pieces spontaneously reassemble into a whole glass, although this doesn't happen in reality due to the second law of thermodynamics. This principle is deeply rooted in fundamental physics, particularly in classical mechanics and quantum mechanics. However, when we introduce thermodynamics into the discussion, things become more complex. The second law of thermodynamics states that in an isolated system, entropy, the measure of disorder, always increases over time. Thus, while the equations of motion might be time reversible, the actual processes involving entropy are not. White holes as time-reversed black holes. Now, let's connect this idea to white holes. In many ways, white holes can be viewed as time-reversed black holes. Black holes draw matter and energy in, leading to an increase in entropy as they consume and compress everything into a singularity. In contrast, white holes, by their very definition, would expel matter and energy, potentially decreasing entropy in the surrounding environment. This time reversal perspective opens up intriguing possibilities. If black holes represent the ultimate endpoint of gravitational collapse and increased disorder, white holes could symbolize a cosmic reset, releasing organized matter back into the universe. This leads to a paradox. If black holes increase entropy, how do white holes fit into this framework without violating the second law of thermodynamics? Implications for thermodynamics and entropy. The implications of this relationship are profound. If white holes were to exist, they would challenge our understanding of entropy and the arrow of time. Traditionally, we perceive time as a one-way street, moving from order to disorder. The idea of white holes suggests that there could be pockets of the universe where matter is reintroduced in a more ordered state, potentially reversing the local increase in entropy. Furthermore, this raises questions about information conservation. In the context of black holes, the information paradox posits that information about matter swallowed by a black hole may be lost forever. If white holes exist as time-reversed entities, could they serve as a mechanism for the retrieval of that information? This is a topic of ongoing debate among physicists and has significant implications for our understanding of quantum mechanics and the nature of reality. Overview of theoretical models. The concept of white holes arises from the equations of general relativity, which predict not only black holes, but also these hypothetical regions that emit matter and energy. One of the first models that suggested the existence of white holes emerged from the work of physicists exploring the nature of black holes. These models often describe white holes as the time reversal counterparts of black holes, leading to the idea that they could exist in a connected framework. One notable model involves the idea of wormholes. Theoretical physicists propose that a black hole could be connected to a white hole through a wormhole, creating a tunnel through spacetime. While this idea is captivating, it faces significant challenges. Wormholes require exotic matter with negative energy density to remain stable, and such matter has yet to be discovered. Another intriguing hypothesis involves the bounce cosmology model, which attempts to address the Big Bang singularity. In this framework, our universe could have emerged from a previous collapsing universe, with a white hole representing the point of transition. This model suggests that rather than a singular beginning, the universe goes through cycles of expansion and contraction, with white holes serving as the birthpoints of new universes. Key physicists and their contributions. Several prominent physicists have contributed to the conceptual development of white holes. John Archibald Wheeler, a pioneer in theoretical physics, was instrumental in advancing our understanding of black holes and their implications. He introduced the term black hole and explored the relationship between black holes and quantum mechanics, paving the way for discussions about white holes. Kip Thorne, another key figure in this field, has also explored the implications of general relativity and the nature of space-time. His work on gravitational waves and black holes has been groundbreaking, and he has speculated on the potential existence of white holes as part of the broader framework of space-time phenomena. Thorne's research emphasizes the interconnectedness of black holes and white holes, suggesting that they could be part of a larger cosmic narrative. Current status of research. Despite the theoretical models and intriguing hypotheses, the current status of research on white holes remains speculative. Unlike black holes, which have been observed and studied extensively, most notably through the Event Horizon Telescope's imaging of a black hole's event horizon, white holes have not been detected. This absence of empirical evidence presents significant challenges in proving their existence. Researchers are actively exploring the implications of white holes within the broader context of astrophysics and cosmology. Some physicists are investigating potential observational signatures that might indicate the presence of white holes, such as unusual bursts of radiation or the behavior of matter near black holes. These studies aim to bridge the gap between theory and observation, seeking to uncover any hints of white holes lurking in the cosmic tapestry. Challenges in proving white holes. The primary challenges in proving the existence of white holes stem from their theoretical nature. The laws of physics, as we currently understand them, do not provide a clear pathway for the empirical detection of a white hole. Additionally, the exotic conditions required for their formation and stability pose significant hurdles. Moreover, the relationship between black holes and white holes raises questions about information conservation, entropy, and the fundamental laws of thermodynamics. Addressing these questions requires a deeper understanding of quantum gravity and a unified theory that can reconcile general relativity with quantum mechanics. Representation of white holes in science fiction. White holes may not be as prevalent as black holes in popular narratives, but they have certainly made their mark. In science fiction literature, white holes often serve as metaphysical gateways, representing the possibility of escape, rebirth, or access to other dimensions. For instance, in some stories, a white hole might act as a portal through which characters can travel to alternate realities or distant parts of the universe. One notable example is in the novel The Forever War by Joe Haldeman, where characters encounter phenomena resembling white holes in the context of interstellar travel. These narratives often explore the implications of such cosmic entities, raising questions about time, existence, and the nature of the universe. Comparison to black holes in literature and film. Black holes, in contrast, have been extensively explored in literature and film, often depicted as ominous and mysterious forces. Movies like Interstellar and Event Horizon portray black holes as gateways to unknown realms, with intense gravitational effects that challenge the characters' understanding of time and reality. These representations tend to evoke fear and awe, emphasizing the dangers associated with approaching a black hole. In comparison, white holes are usually presented in a more abstract or philosophical light. They often symbolize hope or renewal rather than danger. For example, in the animated film The Cat from Outer Space, the protagonist travels through a white hole, suggesting a more positive and adventurous narrative. This contrast highlights the differing emotional responses that black and white holes evoke in storytelling. Public perception and misconceptions. The public perception of white holes is often clouded by misconceptions and a lack of familiarity. Many people associate black holes with destruction and chaos, while white holes are seen as more enigmatic and less understood. This disparity can lead to confusion when discussing their roles in astrophysics. One common misconception is that white holes are merely the opposite of black holes, without recognizing the deeper implications they carry within theoretical physics. While they are indeed viewed as time-reversed counterparts, the concept of white holes encompasses complex ideas about entropy, the nature of time, and the fabric of space-time itself. Additionally, the scientific community has not yet produced conclusive evidence for white holes, making them a more speculative and abstract concept. This lack of empirical support contributes to their lesser representation in mainstream media compared to black holes, which have been observed and studied extensively. The appeal of cosmic mysteries. Despite these challenges, the allure of white holes lies in their potential to inspire curiosity and wonder. They invite audiences to ponder the unknown and explore the limits of our understanding of the universe. As scientists continue to investigate the nature of black holes and their theoretical counterparts, white holes may capture the public's imagination in new and exciting ways. As interest in space exploration and astrophysics grows, so too does the potential for white holes to find their place in popular culture. Future films, books, and media may delve deeper into these cosmic enigmas, offering fresh interpretations and narratives that challenge our perceptions of time, space, and existence. In summary, while white holes may not have the same level of representation in popular culture as black holes, they still evoke a sense of curiosity and wonder. Their portrayal in science fiction often emphasizes themes of exploration and renewal, contrasting sharply with the ominous nature of black holes. As our understanding of the universe evolves, white holes may become more prominent in narratives that inspire us to question the very fabric of reality. Recap of the fascinating nature of white holes. White holes, as we've discussed, are envisioned as the time-reversed counterparts of black holes. While black holes absorb matter and energy, creating regions of intense gravitational pull, white holes are theorized to eject matter and energy into the cosmos. This duality presents a compelling narrative about the nature of existence, entropy, and the flow of time. The idea that these two entities could be interconnected through wormholes or other mechanisms invites us to think beyond our conventional understanding of space-time. Moreover, white holes challenge our perceptions of reality, offering a glimpse into the possibilities of alternate dimensions and the cyclical nature of the universe. They embody the questions that lie at the heart of modern physics. What happens to information swallowed by black holes? Can matter be reborn through white holes? These questions inspire scientists and storytellers alike, bridging the gap between rigorous science and imaginative speculation. Their role in understanding the universe. The theoretical exploration of white holes is not merely an academic exercise. It has profound implications for our understanding of the universe. By studying these cosmic entities, we glean insights into the fundamental laws of physics, particularly the interplay between gravity, thermodynamics, and quantum mechanics. White holes could provide a new perspective on the nature of time itself, suggesting that the universe might possess a deeper symmetry than previously thought. Furthermore, the investigation of white holes compels us to reconsider our models of cosmology and the evolution of the universe. If white holes exist, they could serve as mechanisms for the emergence of new cosmic structures or even new universes, challenging the traditional narrative of a singular beginning with the Big Bang. This possibility opens up a plethora of avenues for theoretical research and invites speculation about the multiverse and the cyclic nature of cosmic evolution. Future research directions. Despite the allure of white holes, the journey to validate their existence is fraught with challenges. As it stands, empirical evidence for white holes remains elusive. Current research focuses on theoretical models that explore their properties and implications. Researchers are investigating potential observational signatures that might hint at the existence of white holes, such as anomalous bursts of energy or unusual cosmic phenomena. As technology advances, particularly in observational astrophysics, we may gain new tools to probe the mysteries of the universe. Future telescopes and gravitational wave detectors could provide insights that either support or challenge the existence of white holes. Additionally, interdisciplinary collaborations among physicists, cosmologists, and astronomers will be vital in bridging theoretical models with empirical data. The quest for empirical evidence. Ultimately, the quest for empirical evidence of white holes represents a broader journey into the unknown. As we push the boundaries of our understanding of the cosmos, white holes remind us of the wonder and mystery that still exist in the universe. They invite us to question our assumptions, challenge our knowledge, and embrace the unknown. In conclusion, while white holes may currently reside in the realm of theory, their implications resonate deeply within the fabric of modern physics. As we continue to explore the cosmos, the search for white holes will undoubtedly lead to exciting discoveries, further enriching our understanding of the universe and our place within it. Thank you for watching. We hope you enjoyed today's video. If you did, don't forget to hit that like button and subscribe to our channel for more exciting content. Your support means the world to us. We can't wait to see you back here for our next adventure. If you have any feedback or ideas for future videos, drop them in the comments below. Until next time, take care and stay awesome. See you soon.